Hi, Dr. Ashison here. We're still on chapter 2, and now we're going to start talking about, this is our third video, and we're going to start talking more about the retina, and specifically about the photoreceptors in the retina. So, again, here's our visual system. Where we are now, you can see the retina is that yellow area in the eye, and we're going to be talking about the retina. We're going to be talking about the fovea, which is the red area, and we're going to talk about how that information gets into those neural signals that you see that will take us in to the brain for chapter 3. So the retina is really kind of the doorway to the neural system. Okay, so the retina is where we see light is passing through the other layers of neurons, and I'll show you that in a second, in the retina, and it strikes our photoreceptors. Our photoreceptors are our primary sensory receptor. So this is the sensory receptor that is converting that, in this case, electromagnetic radiation, light, into brain waves, okay? Into neural signals, into the brain, okay? So this is, light is striking these photoreceptors. And again, these photoreceptors are a primary visual sensory receptor, and this is where light is transduced into neural signals. This is where the physics is happening, and we see that the light, the energy of electromagnetic radiation, is being converted into neural signals that our brains can understand. So there are two classes of photoreceptors we have, rods and cones. In this picture, the rods are tinted yellow and the cones are tinted purple. And you can kind of see where they're getting their names. The rods are rod-shaped and the cones are more cone-shaped. So their names come from their shape. Here's another picture of rods and cones. You can also see that the rods are typically longer than the cones are, but we still have the nucleus and the synaptic terminals, and then this outer segment is where the kind of the magic's happening in terms of that conversion of electromagnetic radiation into neural signals. The fovea is another part of the eye that we didn't talk about when we were talking about the eye, and that is really the center of the retina. So when you are focusing on something, you are foveating on something, and that means that you are putting that image on your fovea. You are looking directly at it. So if I am focusing on this picture of the fovea, I am foveating on it, and I am putting it on my fovea. So this is where the center of our gaze hits our retina. So again, this is where we're focusing. When we're focusing our vision system on something, that is what we're doing. And what we have in the fovea is a really high density of cones. So we have lots and lots and lots and lots of cones here, but no rods. And we'll get into why that is in a second. But what we have again is a lot, and you can see that here the cones are different colors, but we see they're all cone shaped. And in this picture, we don't really have any rods until we're outside of that dip, okay? And so we're outside of that fovea. So in terms of the retina, and this is all of the retina, we have several different layers of cells. So in this video, in this picture, you can see it. The retina is this top layer, and there's layers of cells that the light has to go through to get to the rods and cones. Okay, and then that information goes back through those cells in terms of neural signals now, and then we'll go into the optic nerve. So here are the layers of cells, and there's a nice little, way to remember, rub bag. Like you can do RH, like blood factor, however you want to think about RH, but RH bag. And this gives us the order of the cells, okay? And this is going to be important. So, and I've color-coded it for your memorization ease. The R stands for receptors, okay? And those are the rods and cones. Remember, those are our primary sensory receptors in the visual system. So R is standing for receptors. And you can see that they are that blue and that kind of teal color. And those are where the light is being transduced into neural signals. That's where the magic's really happening, okay? That information then passes to another kind of cell, which is called a horizontal cell, okay? You see these are the red cells here. And you can see that many rods and cones are all connected to this one horizontal cell. Bipolar cells in this picture are the green ones. And so we're going to see those will be next in line. Amacrine cells are next. We have the purple. And finally, we're going to have the ganglion cells. And we're going to have a whole nother video that talks about that, retinal ganglion cells. So we'll also call them RGC, retinal ganglion cells. And so those go into those retinal ganglion cells, and you see all of those axons. And you can see this in this image. It says axons of the optic nerve. So this is where the information, the final stopping point for it to get pathway out to the brain, okay? So the information gets transmitted through all of these cells, and it comes out of the brain through the optic nerve, or into the brain through the optic nerve, and the optic nerve is made up of the axons of these RGCs. Okay, so the photoreceptors in the retina, again, are those two different types, the rods and the cones. Both of them are transducing light into neural signals. They're just doing it differently, and they do it with different kinds of light. So rods are more sensitive in lower lights, okay? This is your kind of your night vision. Your rods are your night vision. They have really poor acuity, okay? So this is, you're not seeing really well at night, right? You can see, but your acuity is going to be very, very diminished. They provide very little information about color, if none. So they have very, very little information about color, and there's only one type of them, and we'll show you this on the next slide. Cones, on the other hand, are kind of the opposite. They are providing a lot more information about light. Okay, this is where we see the differences in color, because remember, light is differences in color, different wavelengths, and the cones are going to pick up on those different wavelengths. Okay, this is going to give us greater acuity as well. And because they're going to pick up on different wavelengths, there's going to be 3 different types of them. Okay, so again, rods are really our night vision. This is where we can see in low levels of light, but we can't see super great. We are not nocturnal, and so we can't see very well, and they don't have very much information about color, and I've got an example of that in a second. And because they're really just focusing on this dim light, there's only one type of them. And again, because they're not interested in color, there's only one type of them. Whereas cones, again, they are interested about color. They're telling us more about light. They're telling us more about the differences in light. And so there'll be 3 types. So here is a graph that shows you we have wavelength across the x, and we have relative sensitivity across the y-axis. Our gray line, our gray curve, is our rods, okay? And our rods are really focusing in low levels of light, and it kind of goes the majority of the spectrum in terms of color, which means that it's not differentiating between colors very well, because it is going, because it does have a pretty big range. But again, these are really only working when we don't have much light to work with, okay? And we don't get great acuity from this. There's a launchpad activity on this that's really great that helps you walk through the different kinds of cones and rods. So cones, there are 3 different kinds, and again, they're corresponding to different colors, specifically different wavelengths. Shorter wavelengths are mostly done by S cones. S stands for short, whereas M cones and L cones, medium and long cones, are dealing more with the medium lights and the longer wavelength lights. And again, do the launchpad activity. It really helps describe these phenomena really, really well. Better than listening to me talk about it. Okay. So more about rods and cones. There are 20 times more rods than cones. So while as our cones are really good for acuity, and our cones are really telling us about different colors and those sorts of things, we have way more rods than cones, okay? Now, those cones are really focused on the fovea, and where our rods are really going to be helping us with periphery vision. So even if you're not looking at something, if you're foveating on something, you're looking at something, you're still seeing things in the periphery. That's being done with your rods, okay? And so that's one of the reasons that there are so many more of them, is because the majority of the rest of your retina is made up of cones. There are some rods of rods. There are some cones in there, but rods are doing dark vision and they're doing periphery vision, whereas cones are really primarily focused in that fovea, and that's where we're getting our acuity when we're focusing on something. That's where we're getting the differences in color. And again, the distribution patterns of rods and cones really reflect their different functions. Cones are for high acuity, so you can see really well, daylight vision. Rods are for this low acuity, but they're very light sensitive in night vision. So a good example of this is my daughter gets up for school pretty early in the morning. Her bus picks up at like 6:50. Today we weren't taking the bus, but she still got up at 6:45, and so it was still dark in her room, and we didn't turn on the lights as I was getting her dressed. So this is the shirt she chose to wear this morning. She's a big fan of Pokemon. Pokemon Go has not helped that any. So she was putting this shirt on this morning, and I was helping her get it on. And it's dark. I've been up, I think, 5 minutes more than she had, so I think I got up at 6:40. And I was putting this shirt on her, and I was putting it on, and it looked like it had a stain on it. And I was like, what are these black lines? Turns out those black lines weren't black lines at all. They were the stripes and the black ear tips on Pikachu. So if you're not familiar with Pokemon, he is the Pokemon that is on the lower right-hand corner of her shirt, the yellow one with the stripes on his back. What I was seeing was those brown stripes and those black ear tips. That's all I could see. I couldn't really see the comparison, and I had to really look at it for a little bit before I could get any more information. Again, that's because my rods were doing the work. It was dark in her room. The only light was a night light, and it was a blue night light, so it really wasn't helping us out much. And so it was really dark in her room. And so I didn't have very good acuity at all. And I had very little color information. I pointed this out to her, and she's like, no, I can see that he's yellow. And I said, well, can you? And then the more she thought about it, she was thinking that was more of that top-down processing. She knew that Pikachu was yellow, so she thought he was yellow. And we talked about the color of her shirt, and she said, she's like, well, my shirt's blue. And I said, yeah, it's blue. I said, but can you really tell that it's blue right now? Because again, we're sitting in the dark and we've just woken up. And she's like, no, it kind of looks white. So again, that was kind of a difference between top down and bottom up processing. Bottom up, our sensory receptors were telling us different information than top down that we knew to be true because we'd seen this shirt in the light. Okay, so some more on the anatomy of the eye. So we talked about those retinal ganglion cells, and you can see them here, where those axons are going out as our optic nerve, okay? And so you see here on this image, it says ganglion cell fibers. Those are those axons going out of the nerve. Where this happens is the optic disc. Okay, the optic nerve leaves the eye and the optic disc. This is where those axons exit the eye. The problem is because these axons are exiting the eye, there are no photoreceptors there. So you can't see. There's nothing to get this information at the optic disc. This is also, because of this, called the blind spot. Now, remember that optic nerve is just the bundling of those axons from those retinal ganglion cells, and they exit the eye through this optic disc. So the optic disc is, again, where those axons from the retinal ganglion cells leave the eye and enter the brain. There is not a single photoreceptor there at all, okay? So any image that hits on that part of the eye cannot be sensed. However, when you are looking at things, you don't see all big hole in the middle of what you're looking at. And this is because your visual image is automatically filled in. It takes the information around it between those two eyes, and it kind of averages it for you. Again, there's a great Launchpad activity. I had a lot of fun doing it. Granted, I'm a bit of a nerd, but I had a lot of fun doing it. So please do the blind spot Launchpad activity. It will really help with this as well. The final thing that I want to talk about in this section on the photoreceptors is dark adaptation. So when we talked about in the first chapter about the method of adjustment as a way to detect sensation and perception, to measure this, this process is being used here to find out about dark adaptation or light adaptation. So light adaptation is when your eyes are going from the dark to the light. You're having to adapt to the light. And in approximately 1 minute, you're doing quite well, okay? So my eyes going from completely asleep, meaning dark, to awake, they were still waking up and my visual acuity was improving, okay? They were doing better after a minute. But remember, when I was looking at my daughter's shirt, I hadn't been up 10 minutes. So they weren't fully adapted to whatever little light I had anyways. So there was a lag there. Dark adaptation is where we have light to dark, okay? So you're going from the bright outside to a dark movie theater. This takes a lot longer to do. It can really take up to 30 minutes to become fully dark adapted. Okay, so here in this graph, you see the minutes in the dark across the x-axis and the brightness of the light that's visible on the y-axis. So as the light gets dimmer, you see that it's taking longer than minutes in the dark. So we need more brightness in less amount of time. So the longer that you're in the dark, the less light you need to be able to really see. And you can see that in this graph, okay? And what we have here is kind of a switch over between cones and rods too, okay? So the green line is dark adaptation for rods only. So this is, again, going from a light room to a dark room. And at the beginning, the rods are needing a lot more light to do their job, okay? Because they just kind of got turned on. They just said, oh, wait, now we need to help. Whereas the red line is the cones only. And the cones are still kind of working. They're still trying to help out. But they don't do well in dark. And so they pretty much kind of shut down. Their maximum sensitivity is not great. Whereas the maximal sensitivity for the rods really is. I mean, if you look down there, I mean, we can have very, very, very little light. And when we're fully dark adapted, we can still see that light. And then the blue line is the average of the two. It's where the overall dark adaptation, and where we see that little kind of uptick in it and then that back down is where we're switching from primarily trying to use our cones to trying to use our rods. So the switch between those here is that rod cone break. So some of what was going on this morning was also a little bit of light adaptation. So again, my eyes were closed, and so I hadn't had much light. Even that little light that was coming on from the night light, it was still causing more problems in my vision. So when I first looked at Pikachu and just saw black lines, that was part of the issue. Whereas when I looked at him, another minute later or 2 minutes later, I could start to see the rest of Pikachu. So again, some of that was that issue of light adaptation as well. Okay, well, thanks, and I'll see you in the next video.